I'll start. I'll just kind of quickly summarize where we are, and then finish up the talk that I was giving last time. So recall this. I kind of cast it as a theorem A and theorem B that Peter talked about, which built on what Clark talked about. Theorem A is that you can characterize constructible sheaves in terms of exit path categories or enter path categories, which is just it's opposite. And I just wrote the expression because the more times you see it, the more times, or then it becomes, it stays in your mind longer. And that the argument for that result, when maybe slightly tweaked, works equally well if you look at sheaves valued in some, let's say, presentable infinity category V. Just note. So that's theorem A, and theorem B was is here, this decollage result, which says that the category of P stratified, I'm just saying for now, homotopy types, though there might be better terminology than P stratified homotopy types, can be cast as a full subcategory of pre-sheaves on the subdivision of P. And I wanted to emphasize, and maybe Peter did at some point, that it's an observation after theorem A plus B that then the category of constructible sheaves on X can be described as a limit of local systems of, on these kind of iterated links, which is a really explicit description of constructible sheaves. For example, if P is just bracket 1, then its subdivision, op, co-represents spans. And in that case, this is just saying that a constructible sheaf on a P-stratified space are compatible local systems given by a span of spaces. It's pretty nice. So I put these tabs as I was motivating last time, a global version of theorem A, and I just wrote the answer here. This is a theorem that appears in this this paper, Local Structures on Singular Manifolds, with John Francis and Hiro Tanaka.
It looks like David froze. Let's see if he comes back. Let's see. Oops, okay, all right, it looks like David froze, so I think maybe he's logging off and logging back on or something like that. Can everybody hear me okay? Just
Yep.
thinking.
Yep.
Okay.
Yes, no problem.
All right, okay, then I think it's probably on his end, okay. Yeah, how's everybody doing?
All right. All right.
Well, I can use this opportunity to emulate that a couple of my students stayed up until 2 a.m. to listen to her undergraduate infinity category talk and are raving about it. Very excited.
Oh, wow.
Well, I mean, really, that didn't go very well. I needed about another half hour. So I should apologize for not really getting to the punchline, but.
It's pretty
They
high
were
praise.
very excited.
Welcome back.
They were very happy.
Well, you can let them know. I mean, I'm actually.
Are we all, can you see me?
We can
Yeah, we've got your screen.
So, shoot. Can you hear me or see me?
Yep.
Yeah, I can hear and see you.
I'm gonna. I'm going to turn my video off so that to save some bandwidth, as suggested by Joey.
Okay.
So if that happens, maybe again for more than 5 minutes, I suggest that Clark, you take over.
Will do.
Sorry about that.
I was going to try and state your
Okay.
theorems, but I couldn't quite do it.
Okay. So all right. So what I'm going to talk about today is this theorem, this global theorem, and it says that that sheaves on the entire category of singular manifolds, just like theorem A, the local version, are pre-sheaves on a stratified homotopy type, which does not appear as the exit path category of any like any conical stratified space to my knowledge. It's just a priori stratified homotopy type of all singularity types, in quotes. So that's, oh dear. Okay. And then one can upgrade that to have a similar result where you specify the singularity types, and there's a similar result for that. And those specified singularity types could even be structured in a certain sense that I might talk about if technical difficulties don't abound. And then theorem B, which is a point set version of the homotopical version previously, which is, and I hope this is a reminder from last time, which are point set constructions of those iterated links over here that I just called links of I, just for short. And this is a big complex diagram, but it's a diagram entirely in a point set version of a category of stratified spaces. And I put little pullbacks and push-outs and stuff for what is push-out and what is pullback, etc. So these are two theorems that are true for a class of structured stratified spaces called conically smooth stratified spaces, which I was getting toward in the last talk. So a feature of this point set description up here is, and this is a question that I'm often asked, that's why I'm going to address it now, is can you define conically smooth structures in terms of locally arranged spaces? And the answer is, of course, is yes. And these are, one can go about it one way or the other, but I don't see a way to avoid the essential math ultimately of just saying what a derivative is, essentially. And I wrote a pullback, at least on global, on global sections of these structure rings. So this is a feature that this class of conically smooth stratified spaces possesses. And there's the advantage here is that the three terms involved in the pullback involve stratified spaces of less depth. And therefore, and in this way, you can kind of induct on depth to access ultimately what's conically smooth functions on a given stratified space in terms of conically smooth functions, or sorry, smooth functions on ultimately smooth manifolds with corners. So that's the advantage of, or that's a takeaway of theorem B. Also, to connect it with the theorem B, the homotopical theorem B, I just wrote this, which is on the left-hand side, the link of two strata appearing on the over here in red, that links of I. If I consists of two elements, P and Q, P less than Q, is that flag. Then there's a homotopy equivalence between underlying spaces of the link mentioned in this previous theorem B. And that homotopical link compatibly with the two strata by this map pi and gamma appearing in this purple diagram up there. Okay, so those are the theorems. And then today I'll outline what conically smooth means, and then I'll say what this, this cool stratified homotopy type basic BSC is.
David, may I ask a question?
Yes, so while you ask, I'm going to charge my pen. So the screen share is going to stop. It'll come back. And I swear I'm still here.
So
Yeah, please go ahead.
what does taking C infinity correspond to on the homotopical side?
Oh, I don't know. It might even be meaningless.
Okay.
Yeah, it's a, we could ask the question just for smooth manifolds, and C infinity functions on a smooth manifold has meaning per the definition of smooth manifolds and smooth functions, etc. But it does not have meaning if you only remember the underlying homotopy type of that smooth manifold. Let me know if that missed the question.
I think that's fine. Yeah.
All right, are there any other questions? Okay. So, I was talking last time about how to get a handle on like even what I'll be meaning by a singular manifold, etc. And I hope you remember that, just to help navigate to have an example in mind where we're going. But now let me define what we call C0 singular manifolds. So here it is. It's convenient to say not what a single one is at a time, but what the entire category is. So that the category of C0 singular manifolds is the smallest full subcategory of that of paracompact Hausdorff stratified topological spaces. So said here, and this is just notation for this ordinary category of paracompact Hausdorff stratified topological spaces. Say it's the smallest one with these 5 properties. So first off, the empty set stratified by the empty poset is in there. These are the minimal features that I would contend any category of stratified spaces would possess, and that's how we'll, and so this was that prompts that motivates the definition of C0 singular manifold here. So empty set is an example, sure. Next, if X and Y are 2 examples, then their product stratified by the product poset is an example. Also, if you have an example which is compact, the open cone on it is another example. Also, if you have an example, X, and an open subset thereof, then in a standard way, U inherits a stratification, and that too is an example. And then kind of conversely, if you have a stratified topological space, which is open, that admits an open cover by examples, then it is an example.
I think
so
4
we can just
implies,
explore.
Yeah, I think 4 implies 0. Sorry.
By taking the empty open cover.
Empty open cover. So the condition holds, and then the union of the empty covers the empty set.
Why are you sorry, Ezra?
because it's a trivial remark.
Oh, that's a good point.
It's also implied by 3, right? Once you have them.
Gosh. Also, there's redundancy between 1 and 2. Yeah, there's no problem. But these are good points. So note
Oh,
that
but I do have
manifolds are in
a
here.
serious question, which is about 4.
Uh-huh.
So in 4, the entire story is over a fixed post-it, or is
No.
it more?
So I was intending to not really address that, but I'll say some comments here. Is right. So X comes. There's an understood poset with X, and the poset for U will not be equal to that poset. So what is the poset for U? Well, it's there's a formal construction given an open subset of a stratified space, stratified by P. You could start off by saying, well, then U is also equipped with a continuous map to P with the Alexander topology, certainly. But now it might be the case that map is not surjective. So, some strata are empty. Okay, so discard the elements in the poset that have no pre-images. It might also be the case that some strata are not connected. Okay, well then just enhance the poset so that an element of the new poset will be a pair, an element of the previous poset together with connected components of the pre-image. So actually that takes care of the first point as well. And that will be the poset to take that stratifies U. Yeah, and it will also have the feature. Yeah, that's right. So it turns out. Actually, I'm not going to make that comment until later if it comes up. Right. So the poset for U is different from the poset for X through this formal construction that ensures that every stratum is connected in particular.
So in this, are you always working with stratified spaces where all the strata are connected?
So by strat top here, I don't need to mean that. But as a consequence of this definition, namely how the specifics of how I said that U becomes an example, and also actually the specifics of how X becomes an example if it's openly covered by U's, like what the resulting stratifying poset is, which I haven't explained here. The specifics of what those stratifying posets are will then it is a feature of this definition, but not part of the definition, that every stratum will be connected. That's right. Is that addressing your question, Peter? Okay. Okay, so unless there's a call for some more details there, I'll move forward, and I'm happy to go into details. Okay, so let's now observe that there's a standard Grothendieck topology on this category of C0 singular manifolds, just given by open covers in the standard sense of open covers. And an observation is that these basic kinds form a basis for that Grothendieck topology. That's a consequence of this definition of these criteria. Imagine how you would show it, how you would prove a statement like this. Well, the definition of this category as the smallest with properties makes it easy to prove stuff. How would you show it? Well, consider the full subcategory of this. consisting of all those objects that admit a basis by these. There gets to be a little bit of induction or of a circularity, it seems, but one can improve that to proceed by induction on dimension, on topological dimension. Nevertheless, one can show that the collection of those objects that admit a cover by these possesses these 5 properties, and so it's true.
So we have to check, for example, that the product of 2 cones is a cone?
Yeah,
Something.
exactly. And there you'll use that the product of 2 cones is the cone on the join. Yep.
Yes, great.
Yeah, exactly. That's the key. I'll just record that here. Ezra's comment. So key sub-observation is that the cone on a product is isomorphic to the cone on the join, where the join is endowed with a stratification in a standard way. Yep, great. Okay, so how we will proceed to define what a C1 singular manifold is by using these to form an atlas. So these will take the role of Euclidean spaces for defining smooth manifolds or C1 manifolds. But to do that, we have to say what a C1 map between these basics are. So so here's a sketch. Oh, my apologies that purple is a little hard to see. So it's just a little convenient just for our discussion here to say what a self map being C1 is, instead of a map between any 2 of these basics. I think it captures the spirit well enough. So an open embedding from one of these basics to another, we'll say is C1 along the cone locus, the deepest stratum, which is this Ri. If, and I hope this expression looks familiar now, after last time's talk, it's just last time there was not, I was 0. And so some of this translational component could have been neglected, but I'll put it in here, no big deal. And remember, the key for defining derivative at the origin of Euclidean space was to note that there's scaling by the positive reals on Euclidean space. And once we noted that, then that inspired us to define what the derivative of a self map of an open cone is, because all we needed was to know how to scale. And that's something that you know how to do for an open cone. So likewise, for Ri cross a cone, there's an action by translation and scaling. So there's this group of translations and scales that acts on this, and it just translates that factor and scales both factors diagonally. And then conjugating by translation and scaling. If you wonder what I mean by that, here's the expression. Defines.
Can I ask about the numerator in that fraction? One of the phi's has 3 arguments and the other has 2. So I just wondered if you could elaborate on that.
Oh, sure. Yeah. I mean, the cone is a quotient. I should really put here, an equivalence class of this pair. Right?
Maybe if are there more parentheses somewhere, or I don't know. It doesn't just, I can't pass the diagram. Yeah. Okay.
Equivalence class of 0, and I'll just put L, I guess. Yeah. So it's the cone point.
Oh, I see. Right.
Yeah. Yeah, thanks. So I hope that expression looks familiar from differential from calculus. So, so we'll say that this map phi is C1 along Ri if, I mean, the limit of this expression as t goes to 0 exists and defines a continuous map. So if there is a continuous extension. See, I closed up 0 here. And the value on 0 will interpret as the derivative. And I just wanted to note that, notice here the role that those two factors are playing as the tangent bundle of Ri. And in light of that, we'll just regard, this is just notation, that this will regard this as, quote, the tangent bundle of Ri cross the cone of L. This will be this will be a stand-in for what that quote tangent bundle is, what that factor is.
Sorry,
we won't come back to that. Yes?
I have a question about this definition. Do you also need to include that the projection from like X cross R to X, then down to the stratifying poset is in there in your definition? To know that
X?
So in your definition of this, of singular C0.
Oh, up here.
Yeah.
Okay.
To know that these like Ri cross cones are a basis, do you need to include that that X cross the real line is in the subcategory if X is?
So
is that 2
so
plus
that's
3?
Yes, I didn't detail the oops, plus 3, you're right. So how do you get the reals is the question.
Oh, you're saying it's the open part of the...
Yeah, check, this is worth, I think it's worth going through a little bit. So the fact that empty is in there, that implies, and it's compact, the cone on the empty is in there, which is point, right? Which implies then the cone on point is in there, which is R greater than or equal to 0, stratified by 0. And then, so this is item 2, and then that implies
and then by
that
3.
R greater than 0, yeah. By 3, yeah. Yeah, a good question. I should have, I even had in mind that I would say why manifolds are in there. Yeah. So then we get that's in there, and then so R greater than 0 is in there, and therefore from by products we get the Euclidean spaces are in there, etc. Yeah, good. Thanks. Okay, so I hope that this looks familiar. It's just to take derivatives in calculus, all you use was translation and scaling. And then you conjugate by that, take a limit as the scaling parameter goes to 0, hope that that limit exists, and just when it does, that's what it means to be C1. Now, allow me to sketch a definition of what it means for a map between two things to be conically C1. See up here, I just said conically C1 along Ri. And I'll just say it's for all, so for all open embeddings from a different basic, the resulting map is, and now it starts to bifurcate into a bunch of induction stuff. So you have to prove lemmas to even make sense of this, which is why I'm just giving a sketch. I don't really, I guess I just don't feel like dragging us through the logic here. But you know, it's possible that this composite map avoids Rj altogether. And in that case, this composite map lies inside of Rj cross an open interval across K. And by induction on the depth of these stratifying posetsets, you've already said what it means for that to be C1. So then by induction, you can reduce to the case where this map hits the cone locus, which is the RJ cross cone point. And in that case, you can argue that it falls into the consideration of this definition up here. And then you say that it's C1 along RA. So for this definition to make sense, one proceeds by induction on L and K. And hence, if you looked at the paper, hence the reason for the rather opaque definition of what conically C1 means, because the very definition goes by induction, where you're simultaneously defining what the condition of being C1 is with what it means for an object to have a C1 structure. So unless there's comments, I'll just keep moving forward. The key math, though, that's just getting bootstrapped up is just, again, realizing that to take derivatives, you just have to know how scaling and translation act. Okay, so continue with this sketch definition. Once you know what it means for a map between basics to be C1, imagine we're talking about what it means for a map between Euclidean spaces to be C1. Then you have grounds to say what a C1 manifold is, right? And what is it? It's we can say topological manifold together with a C1 atlas. And what a C1 atlas is a collection of open embeddings from your basics that form an open cover, but it's actually convenient to say a little better. It forms a basis for the topology of it. Together with demanding that the transition maps are C1. And we know what that means now, or it was sketched, because we know what endomorphisms of these what it means for an endomorphism of these basics to be C1. That's what was definition sketched up here. So I hope this feels really similar from smooth manifold theory. That once you know what the local type is, and what it means for an open embedding from one local type to another to be of some condition, like C1, then you can define manifolds for those local types. That's what a C1 singular manifold is. And an example I should have inserted. Here's just some quick examples. Examples are any smooth manifold, or C1 manifold. That gives an example. Another example is the cone on L, where that's a C1 manifold. Another example are things that look locally like that, such as R cross the cone on the circle. So locally like this, let's say, or R3. And this gives rise to that collection talked about earlier of links in three manifolds. And let me say to that so singular manifolds just outlined that locally look like either of these two basics. R3, by the way, is R3 cross the cone on the empty set. So it's one of these types. Singular manifolds that locally look like these two, so that admit an atlas just by these two isomorphism classes, are not exactly links in smooth or in C1 3 manifolds, but rather they're they can be described as PL manifolds together with a PL one-dimensional submanifold properly embedded, together with a smooth structure on the complement, or sorry, a C1 structure on the complement of that link, and a C1 structure on the link itself. So you're not ensured a smooth structure kind of across the link, just from this definition. I think Tomer, you brought that up, or someone did last time. So that's C1, and reflect for a moment on how you define C2, what it means for a C1 map from one manifold, one C1, from Euclidean space to Euclidean space to be C2. That can be phrased, or the one way of defining it is, so recall that you can say that a map phi from Rn to Rn is C2 if it's C1 and then what that gives you is that it determines a continuous map between tangent bundles but then these tangent bundles are in the case of good old manifold theory, just your local type again. So, and you've already said what it means for such things to be C1. So if that is C1, right? So I bring this up because we can repeat this, because up above, and I put in blue notation what the tangent bundle of a basic is. So for us, the tangent bundle of one of our basics, I said, was this really, I guess, the tangent bundle of Ri across the cone on L. And we defined derivative precisely so it determines a map between tangent bundles. So then you just follow the same pattern of definitions as the smooth manifold theory. So that's what a C, and that's what C2, what it means for a map to be C2 is between C1 singular manifolds. And you bootstrap up that to say what a C2 manifold is, et cetera, et cetera.
David, this is
Yes.
Aaron. That's so that's fine. This definition of tangent bundle to give a definition, but just intuitively, it's not like what I would have guessed the tangent bundle to be, right? Like there's no tangent direction in the cone. There's no component in the cone direction.
Oh, this is not the tangent
tangent
space. So what is the map from the tangent bundle to the? This goes down to Ri cross cone, and through this definition, what is that? It's the projection. Whoops, there's off the Ri.
Mm-hmm. Sure.
So there's no tangent direction in the cone direction. Is that
right?
Here?
That's what I was asking. So I mean, is like if I drew a picture of some reasonable looking stratified manifold and then thought about what the tangent bundle would be, I would not arrive at this definition, right? This is tailored specifically to these basics.
I think when a reasonable person might come across this. So Ezra brought up a comment at the end of last time we met, and anyway, one perspective on tangent bundle is that its sections are infinitesimal automorphisms, right? And this notion of tangent bundle is consistent with that, right? because if you have a R1 cross a cone, how could you budge? What's an infinitesimal automorphism of that? It has to just, you can't move R1 off of R1. You have to move it along itself.
Okay, but so this is like an epsilon neighborhood, thinking of it as an epsilon neighborhood of the cone. Like if you're away from the cone locus, like it just feels like even the dimension is wrong. You know, say we take the cone on R0.
Oh yeah, right. This is, thanks. Yes, right. This is, I see what you're saying. And to that, I realized that I neglect my notational scheme was bad, and it's also not. So in the paper, this is addressed. Of course, this is like this restricted to the Ri. It's the tangent bundle restricted to the Ri part. Does that make sense?
Yeah, I think that's what I was asking. Thank you.
Yeah.
It's like the collection of tangent vectors that run in that direction.
That run in that direction, yeah. And,
okay.
Though I wasn't planning on talking about it, and don't intend to, one does not expect for there to be a vector bundle, which is the tangent bundle of a singular manifold.
Well, certainly not a vector bundle, yeah.
What one would expect, right, is a constructible vector bundle in a certain sense. And this is just what the stocks of that look like, right?
Uh-huh. Okay, great, thanks a lot.
Okay, so that's what I had, okay. I'm inclined now to rely on your prior knowledge of how smooth manifold theory is developed, and hopefully I've said enough on which you can flesh your imagination on how C infinity singular manifolds or conically smooth stratified spaces go therefrom. And let me move on to the theorem A and B now. So, so just as we talked about last time, I talked about a category of manifolds of a specified dimension n, and endowed that category, or enriched that category with topological spaces, if you remember. Just the same, one can construct singular. And this is a category whose objects are C infinity, which I will drop in notation and terminology, singular manifolds. The definition, which was just outlined. And then morphisms are C infinity, open embeddings. And endowed with a version of a C infinity topology. And so this is a top enriched category, which then determines through standard formalism an infinity category. And let's just observe that a full subcategory of it is what was talked about last time, is this manifold. It's full on consisting of smooth and manifolds. And that's true for any n. Definition is basic, is the full infinity subcategory consisting of of the basics. Singularity types. In other words, all those of the form Ri cross the open cone on L as you range I and L is compact and one of these. So this is a basic singularity type. Okay, so now I intended to comment that there's a lot of examples of these C-infinity singular manifolds. They're easy to produce. Let me just say in words without writing so let me comment about Whitney stratified spaces. So the definition of a Whitney stratified space is an extrinsic definition. It concerns a subset of Euclidean space, or at least something equivalent to that. Some place where you already have an a priori notion of secant lines, or essentially just tangent spaces. And it makes reference to that ambient notion of tangent spaces. The definition just presented, and the point is that it's intrinsic. You don't need to have an ambient space that already has notions of tangent vectors, such as Euclidean space, to say what a C-infinity singular manifold is. That's advantageous because then it's comprehensible to talk about maps between two things, because you then can make sense of what it means to like kink along a singularity without having to talk about like little fuzzy neighborhoods in that ambient Euclidean space, and how maybe with respect to those open neighborhoods, you're allowing smoothness to fail along these loci, and that's somehow independent of the choice of little thickening, etc. So I think most of us here already appreciate the advantages of intrinsic definitions of the objects that don't make reference to extrinsic data. In particular, in order for defining what maps, and in particular automorphisms of objects are. And it's the classification of automorphisms that is the main result of this theory. So okay, so let me say some of the main results now. Okay, so we know what basic is, and that's one of the key players in the theorem A, the global theorem A that was mentioned. I don't know how to stop that, so I hope nothing embarrassing happens. Okay. Oops. So theorem, and I was calling it key proposition, is that so there's an obvious map from O of I across automorphisms in this category of L to endomorphisms in this category of a basic. I hope that map seems, so it rotates the Euclidean part, and then the open cone construction is functorial for automorphisms. And the key proposition is that obvious map is in fact an equivalence. And it's some mix. What the inverse is a mix of derivative at, I'll just call it the origin. So the origin comma cone point, together with a Graham-Schmidt map. which the Gram-Schmidt map is responsible for seeing O here, not GL, as well as the splitting, which you wouldn't maybe at first expect. So you use that you can take derivatives, just like I talked about last time we met, to know that endomorphisms are actually the same as isomorphisms of the object. And even better is that they're not just isomorphisms of this, but isomorphisms of it are in terms of just isomorphisms of the thing you took the cone on. That's remarkable. So that's the key. Essentially all the definitions are so that this is true. The way that I've talked about this in the past, I don't know if successfully or not, is that this category of C infinity singular manifolds is like the minimal thing, so that you have those 5 properties that define C0 singular manifolds together with this deformation retraction here, which is this key proposition. So this is the most important technical result of that paper and stuff. And it's really what motivated the definitions for everything, so that's true. And this is as monoids in spaces, in the infinity category of spaces. Allow me to just say, as if it's a corollary, though it's not, I don't claim that it's obvious, but as a corollary is that there exists functorial blowups and links. So it's because of this feature, namely that an endomorphism of an open cone determines and is determined by an automorphism of the thing it's the cone on. If you think carefully about it, that has to be true in order to have functorial blowups and links. And indeed, that is true as supplied by this derivative map. So this, I'm just gonna pretty much say, this is our theorem B mentioned above.
David, can I ask a question?
Of course.
It's sort of an idle question. What happens if I think about singular Cn instead of C infinity? Is there some version of this proposition?
Yeah, thanks for bringing that up, because it highlights why we would want to bother to go to C infinity. This retraction is given by taking D. So if you looked at like not C infinity singular manifolds, but CR or whatever, this R would be decreased by 1, So you get something more like, let me see if this can be meaningful. Ought with respect to CR of L, ought, or end with respect to CR of the cone on L, ought with respect to CR minus 1. And there's, of course, this inclusion, that inclusion, and then the derivative would look like this. Is that meaningful to you? Like, you wouldn't get a retraction even.
Sure, thanks.
Yeah. You lose a derivative. Yeah, that's a good point, and that's why passing to C infinity is the thing to do here. Okay, and now also a corollary of that key proposition. Oh my. Sorry, folks. I need to charge my pen again. So another corollary is that we can read this proposition as in particular saying that each endomorphism in this category of basics is an isomorphism. So this category of basics is a stratified homotopy type.
Is this a generalized Reedy category?
By this, do you mean, what are you referring to by
the basics?
I think not. I think very much not.
Okay.
But did you might have had something in mind, like that there's a filtration to it or something?
Yeah, a dimension function or something like that, and that if you either go up or you have an automorphism.
Right. Yeah. No, so that is true what you said, and
yeah.
So
So
I guess
so that's a situation that was studied by Berger and Mordijk. I just want to throw that out there.
And what is this? What's the
so
statement?
they wanted to develop the notion of Reedy. Well, they had up and down, but so this is
Right.
just half.
That's why I say it's not a Reedy
Oh,
thing.
it's not. Oh, I see.
Yeah.
Oh, well, it's generalized Reedy, except that the down is trivial, I guess. Yeah, is just probably the identities or something. So,
but you don't have a. Okay.
Yeah.
Maybe
So their idea is that you get the factorization. You need three things now. You need up, down, and automorphism, which should be a groupoid. So. I don't know. It might be. So they were interested in, I think, dendroidal sets. So not completely unrelated, perhaps. That's, in other words, infinity operads.
Right. Right. And their arity supplies a similar kind of filtration.
Yeah. So they need. Yeah.
Mm-hmm.
Yeah.
At least for non-unital things. Yeah, that's right. Okay, so there's this corollary of that key proposition. It's just an immediate corollary, unlike the previous one. That each endomorphism is an iso, which is what I mean by saying then that infinity category is a stratified homotopy type. Now, there's a theorem, and I essentially outlined the theorem in the case of the category where you replace singular, that infinity category, by manifold sub n. And the same proof works just the same to prove this, to prove theorem A. That global theorem A, which is that sheaves on singular. If you're wondering what I mean by that, speak up. So there's this obvious restriction, which I'll call iota upper star. Denote the inclusion as iota. And the restriction, the functor, is an equivalence between infinity categories. And again, the proof has two steps. First is show.
Wait, there's no constructability here?
The right conic extension. Oh, thank you.
Cool.
I hope, yeah, thanks. Show the right conic extension takes values, which is a functor pre-sheaves. Right, conic extension defines a functor this way. So that's RKE. It's given by the formula that of that was written tagging theorem A. So that's the first thing to show, and that uses the key proposition in doing so. So this uses the key proposition and the key observation, which is the following, which is that, so when contemplating a right conic extension, one contemplates undercategories. Because these are presheaves that we're talking about, these are contravariant functors, so one will end up contemplating overcategories. X. And so this category here, basic over X, is what comes up when contemplating the right conic extension. And the assertion is that this is equivalent with enter of X. Because just think about it. Each point in X has a little small neighborhood about it, which is one of these singularity types. You know, the definition of what we mean by a singular manifold is such that that's the case. So I just indicated that every object here determines maybe up to contractible choices, which are indeed contractible given the key proposition, an object over here. And furthermore, given an entering path, choose a little neighborhood of the start of that entering path, a little neighborhood of the end of that entering path. And just before the moment of entering, pause, and you see a little small neighborhood embedding into a larger neighborhood. That's just kind of a heuristic idea. So there's this key observation. By no means did I just give a proof, but at least it's something that you might believe, which is that. So how would one prove this? Show that both sides carry open cover, hypercovers of X to colimit diagrams. That's true because that's true for enter of X because of the decollage construction. And then it's true, and then use Van Kampen's theorem on the one hand. That's true on the other side, basic over X, because of a partition of unity type argument, and that basic over X is the basics form a basis for the topology. So key in here is to show that there's, I'll put basic delta over X, that there's a localization. That this is the hardest, to show this is the hardest part. And that was actually present in the cases with manifolds as well. I just didn't mention it. So that's the hardest part of this key observation. As a consequence of that key observation, we get this wonderful functor from enter of X to basic. You, so to speak, invert that equivalence, that unnamed equivalence. Yeah. And this is what I'll interpret as the tangent classifier for X. And I will justify calling it that because there's an observation, which is the following. So basic op goes to spaces, in fact, pointed spaces, by sending one of these basics to its one-point compactification, which is a I-fold reduced suspension of the unreduced suspension of L, where you regard one of the unsuspension points as the base point. And then there's a functor further given by, or there's the natural functor to, let's say, spectra. And in this way, it makes sense to contemplate this functor from basic to spectra, which is given by the one above, followed by internal Hom to the sphere spectrum. And what I'm observing here is that, so this is just set up, I guess. What I'm observing here is that for all x and singular, this functor is the dualizing complex. So we might call that omega sub x is the dualizing complex. And I'll put complex in quotes because I'm doing this in spectra, not chain complexes or something. The dualing complex for x. And what's cool about it is it's in light of theorem A, or well, it's a constructible cosheaf on X. So it's on those grounds, for example, that I'm calling, that I feel justified in calling this the tangent bundle. It's because it's linear dual once you linearize is the dualizing complex. And that's saying in better words what I wish I said when I responded to Ezra's comment last time, that there's kind of two perspectives on the tangent bundle of a thing. One is, again, that sections are infinitesimal automorphisms. Another is that its dual is the dualizing complex for it. So this is that other perspective. So that was kind of an aside.
So if could I make a quick remark? So somehow manifolds with corners are a bit like local complete intersections. Their dualizing complex is locally trivial.
Sure.
And what's the general, for you, is that it? If I say, when is the dualizing complex locally trivial, does that single out manifolds with corners, or are there more?
Yeah, I think that's a cool question. I think that characterizes it.
Okay.
I don't know for sure, though.
Actually, there's two different kinds of manifolds. There's manifolds with corners, and there's, you can use orthogonal, orthons, or you could use angles. So there's a subtlety in even the definition of what a.
That's right. That's right.
And so probably you need the orthont
and that
one.
is the.
Yeah.
Yeah, exactly. Yeah.
Okay. Okay, thanks.
So that's a summary of the proof of theorem A, is that together with this purple interjection. So you first identify this, and then and that way you get anyway, and then you show that the unit is an equivalence by showing you now know both sides satisfy descent, and then it's enough to show on a basis for the topology where it's manifestly true. So that's theorem A, and I'll then just indicate, so I'll indicate what the consequence of theorem A is. And then I'm pretty much done. So whoops. Right vibration over basic through the straightening on straightening is given by what we saw in the arguments, is that this right con extension implements once. So how is this given? Well, given now a right vibration, what's the sheaf? It's the one that sends to a singular manifold X the space see, here's the tangent classifier defined just above the space of maps like that. So it's the space. I can interpret that space as the space of this is the space of E structures on the tangent bundle of X. That's just a way of interpreting it.
Mm-hmm.
And another way of interpreting theorem A is that every constructible sheaf on singular manifolds is given by tangential, is given through the from tangential ones. And I'll finish by saying then, so because basic, BSC, is a stratified homotopy type, right vibrations over it are really way more, it's way easier to give examples of those than for right vibrations for a general category. In particular, there's a whole class of right vibrations that are in fact fully faithful subcategories of basic. So note, B fully faithful right vibration. What is such a thing? Well, being fully faithful, it's just specified by a collection of objects of basic. But to be a right vibration is to say that anytime you have a morphism from some other object to one in this collection, the source of that morphism is also in this collection. So this is the same data of a what's called stable collection of singularity types. And so for X in singular, if there exists a B structure, it's unique. And it exists if and only if the singularities of X are in this collection. So this, maybe I'll give this notation, just let's call this E of X. B of X is either equal to point or empty. And it's point if every singularity type of X it belongs to this collection. If X's singularity types belong to B. So in this way, it's so anyway. So an example of such right vibrations then are just where those that select out these. So the theory of singular manifolds with a BON structure is precisely the theory of smooth-end manifolds. A
Right.
theory of singular manifolds with a, so that's one example. And this gives rise to just manifold sub n. Another is if we take B to be the two singularity types of that extended example, like R3 and I'll just say, well, R cross an open cone on a circle. So B is the full subcategory generated by R cross the cone on the circle and R3. If it's full on those, then this gives rise to MFLD 1 inside of 3, if you know what I mean.
Yeah.
Etc. And then the class of examples of right fibrations, which are not fully faithful, are themselves interesting. Of course, there's a factorization system to right fibrations. Every right fibration uniquely factors as a surjective right fibration followed by a fully faithful right fibration. And so, so given a generic right fibration, you can think of that as, first off, its image, so a collection of singularity types which are stable, together with some kind of tangential structures thereon, like a framing, etc.
So for example, complex singularities.
Complex meaning?
Like coming from, so take complex cones instead of real cones.
Yeah, like that, yeah. So that's everything I wanted to, oh, I think Sarah is here, Sarah Yackel.
Yes.
And I just wanted to say that we had a conversation about this once or twice while MSRI was still open. This theorem A, I find theorem A compelling. I see it potentially in other guises. So, you know, if you fix a finite group G, then you can, of course, look at its orbit category, and that's a stratified homotopy type. And in theorem A, this plays the role of basic, right? It's like the, so while the data of G acting on a topological space, let's say in a suitably nice way, so maybe X is a smooth manifold or something, so that, and this is determining an orbifold. This is like, to be consistent with what I wrote, enter. This is the tangent classifier for this quotient to orbit. So this is just an idea that I think would be cool to follow through, to follow up on, is to see theorem A, which is a characterization of sheaves on some class, some site, in terms of just simply pre-sheaves on the collection of all local types. And so I imagine that there could be a story like that here. I just wanted to mention that. I think would be cool, like if Sarah wants to work that out.
That's wonderful.
Okay, well, thanks y'all for your attention.
Thank you, David. This is extraordinary. This is wonderful. Would you be willing to share these notes with us?
Yes, yeah, certainly.
Okay.
I'll do that through the Slack channel, I guess.
Yeah, that'd be perfect. Thank you.
Cool. Yeah.
I know you don't like Slack, but I appreciate it.
No, I think it's a good thing. It's a good tool. I like it.
Could we possibly create also a web page that shadows this and lists and has the files that are accumulating? Just so, because
yeah, that's a nice idea.
the Slack doesn't, as far as I can work. Oh, maybe there is a button that pulls all the files that have been posted. Oh, there is. Okay.
There might be, but I think your larger point is right, that we should probably try to, it's a disorderly kind of place. It's good for sort of chats, but it's not necessarily good for, you know, having permanent records of things.
And when there are enough messages, well, I guess they have a paid version, so it won't be a problem. But
Yeah,
in
so
other groups, they can disappear.
That's right. But so our paid version is meant to last at least through the summer. I got confirmation of that from Hélène. But, you know, after that, it's a fair point. I think it's a good point. Maybe we can actually do it through Shifted, Peter. Or I can do it through Shifted. I'm not going to put that on you. But
yeah, we could definitely do that. I mean, yeah, for sure. It would be very easy.
Cool. Let's see here. What am I doing? I'm trying to join a meeting. All right. So I'm just going to talk for maybe. I'm just going to talk for just a minute, not for very long. I'm just going to share some of the things that I've been thinking about for the past, well, I guess the past 2 years, together with Peter and others. And I'm just going to show some of the ideas that I'm hoping to try and talk us into thinking about. So here we go. Can everybody see that okay?
Yeah.
Okay, great. So this is a little table I made this morning of the different kinds of stories that we've been listening to. And so there's several axes here. First of all, there's the question of you know, the unstratified story versus the stratified story. And then there's sort of different instantiations of this. There's sort of the abstract story. And then there's the sort of story that kind of motivated us early on in the group here, where we were talking about topology. And then there's a story from the point of view of arithmetic geometry, which we touched on briefly, but we didn't dwell on for too long. And then there's, well, I've just been very, very coarse and just written differential topology, and then written the stuff that I learned from David's talk in the past 2 times. So, but I want to emphasize that there's actually a blank here in our understanding, and I think that blank is actually kind of interesting. I think it contains some mysterious information, and so I wanted to just share with you what I think that piece of mysterious information is and how it works. So let me zoom in on some pieces of this. So I'm going to take the position that the sort of story that we were telling ourselves about, you know, this sort of monodromy equivalence between sort of locally constant sheaves on a space and representations of that fundamental groupoid, that's really a story that we should think of as a story about a connected space for now. And then if we want to deal with different connected components, I'll just think of those as different strata of a stratification, which is a little on the boring side, but it's still a stratification. So I'm gonna follow in David's footsteps and work with stratifications where the strata are connected for the purposes of this story. So let me zoom in on some pieces of this. So here we have a connected space, Y, and we're trying to understand something very simple. This is a connected homotopy type, and we're trying to understand something very simple. We're trying to understand the nonlinear representations of the loop space of that space. So equivalently, that's the same thing as just saying that you're looking at functors from Y into spaces, and that's the sort of core object to which we want to compare all the other objects. And so how does this play out? Well, in the case of topological spaces, we learned that those things can be, an example of a category of that shape is obtainable by looking at locally constant sheaves on your favorite connected nice topological space. And then, well, we can push this analogy even further. We can start talking about schemes. So if you've got a nice scheme or variety, then you can look at locally constant sheaves for the Étale side of that. And that thing, again, well, it doesn't quite reproduce a homotopy type, but you have to pass to a profinite homotopy type or something of that ilk. But that this was a perfectly analogous story. And then in the differential topology world, we learned from David's talk that, in fact, you could look at, you actually had a really interesting example of this where you looked at n manifolds, and you looked at locally constant sheaves on the entire site of n manifolds. So that's the nonlinear story. So the nonlinear story is in orange here. But there's a linear story as well that we could start to talk about. And the linear story is pretty well developed. The linear story is that, and remember we talked about this is the Tanakhian duality story. And so the idea is that, well, at least originally it was a group scheme over K, but in our case, since we're, infinity categorical types, we'll be thinking about things like a derived gerbe. K here, in most cases, I'm happy to consider it just being a field of characteristic 0 even. I think there's still a lot to say even in that case. But so what's the idea? So the idea is that you want to, again, think about representations of the loop space of that gerbe. Well, now these are linear representations. So these are representations over K. And another way to say what that is just to say that you're looking at quasi-coherent sheaves over that derived stack. And now, so those are the kinds of the things I want to say are the stuff in this column here. Maybe I'll use a color blue. The stuff in this column here, these are the kind of these are the models to which we want to compare everything. So we want everything to look like one of these in this column. And so what happens in topology is that, well, you look at something like locally constant sheaves on X with values in, say, K vector spaces, or the derived category of K vector spaces. And then you have an associated thing to that, and the associated thing to that is a gerbe, which is kind of like the pro-algebraic hull of the homotopy type of X. Now, traditionally, that's way too big for our purposes. So what people do in practice is they look at much smaller categories. So these are like this category here that I'm looking at. This is like the category of all flat vector bundles on X, if you think of X as a manifold. You might want to go a lot smaller than that. And so you might want to aim for alternatives that look like, I don't know, for example, unipotent vector bundles. Oops, that's too thick. That goes for things like unipotent vector bundles or such things. And there are other examples that I could put here, but I'm just trying to give you a kind of overview of the analogy that I'm trying to pull up. So one wants to consider these things, and then one has an associated object, which, in nice cases, looks like a pro-algebraic group. And by sort of choosing good subcategories, you can get an even smaller pro-algebraic group and really sort of get a grip on that object. And so this is a story that's pretty well established now. This is sort of the higher Tanakhian duality story. Another source of examples of things of this shape is what happens if you take a scheme. Remember, this is our algebraic, this is our arithmetic geometry column. You can take a scheme and you can look, for example, at locally constant sheaves here, for example. You can look at locally constant sheaves for the Étale site, again valued in, say, K vector spaces or the derived category thereof. And you can look at the associated object, which is going to be some, again, like group scheme or gerbe attached to this thing. And that's going to be a massive object. That's going to be an extraordinarily big object. You can, again, cut it down to size by thinking about something smaller like unipotent vector bundles, or you can use this the semi-stable vector bundles in the style of Nori, or, you know, there are various kinds of ways to get a smaller object out of this. But I'm just trying to illustrate the general phenomenon. But now in this story, there's actually a whole other class of interesting objects that we're interested that can be extracted from this, because not only do we have locally constant sheaves on X et with values in some field K, but you also have some other more interesting things that really use the geometry of X in a different way. So, for example, if you're working in characteristic 0, you can start to talk about Hodge structures. And the category of Hodge structures is an example of one of these Tanakhian categories. And the associated group is sort of the Weil restriction for the complex numbers over the reals of GMs. This is sometimes called the Deligne group. And representations of that are the same things as pure Hodge structures. And there's an even more exotic example involving isocrystals. So this is the kind of thing that you have when you talk about p-adic cohomology theories. And the idea here is really that and this is something that I want to emphasize because I think it's a story that I don't know an analog of in topology, although I'm prepared to be countermanded. But I want to say that when you look at the cohomology of your favorite scheme X, that cohomology is you know, it's always taken relative to a certain kind of cohomology theory. So for example, L-adic cohomology is an example of this, or Derive cohomology is an example of this. And then there's some other more exotic things. And the values of the cohomology aren't just vector spaces, they're actually representations of this gerbe that you construct over here by using Tanakh duality. That was actually the original purpose of this Tanakhian story. It was actually the function of it. So and when I'm talking about this, I'm talking about really cohomology right now with just field coefficients. I'm not trying to be fancy about this. I'm just thinking of Weil cohomology theories. So by the way, if you want to see some instances of this well, let's see here. If you want to see some instances of this kind of described in this really beautiful fashion, I really strongly recommend looking at Schultz's ICM talk. Especially well, I can't remember which section, but in Schultz's ICM talk, he really says what a cohomology theory should be, and he describes the entire collection of them using this amazing diagram that I'm not even going to try and reproduce right now, but I can do so at a later time. But the point that I want to make is that what you're meant to do in some sense is you're meant to splice all of these individual cohomology theories together into one kind of integral cohomology theory, which is Harry wants to know how I'm defining a derived gerbe. You should go ahead and interrupt with questions, please. A derived gerbe for me right now, I'm being very vague about it, but I mean that I'm looking at connective affines, so I'm only looking at connective E-infinity rings. And I'm taking sheaves for the FPQC topology. And the gerbe condition is just a local connectiveness condition. And that's all that's the level of specificity I'm working at. in practice, you need more assumptions than that, but I'm just staying ambiguous. And no truncatedness. Okay, so this is again a more or less well-established story. At least at pi naught, it's very well established, and then for higher pi i's, it's you know, there's a lot of interesting stuff going on, but you know, I think, well, anyway, so that's what's happening. So this is the unstratified part of the story. Let me just emphasize. That's the unstratified part of the story there. But I'm interested in now moving down to the stratified part of the story. And that's what we've been talking about so far. So in the stratified part of the story, our models, what do our models look like? Well, we're going to start off with something like a stratified space or stratified homotopy type. And remember, what we mean by that is an infinity category in which all endomorphisms are equivalences. Right. In other words, it's a infinity category with the property that it admits a conservative functor to a poset. Oh yeah, thanks, Peter. I appreciate that. So so what's the model for the kinds of categories that we're going to be interested in? We're looking at functors from that category into spaces. So it's an exact analogy to what happens in the nonlinear story, the nonlinear unstratified block. So now, what are our examples? Well, the first example is the one that we learned about at the beginning of this working group, which is that if you have a nice stratified topological space, then you have associated to it this stratified homotopy type. Peter showed that, in fact, that's an equivalence of homotopy theories, but that stratified homotopy type actually reconstructs for you the category of constructible sheaves. And so constructible sheaves really are just a functor category in the same way that we saw in Peter's talk and in David's talk and again and again. Okay, so now we can try and move to the arithmetic geometry setting, which is here. This column is next. And there what happens is, well, if you've got a reasonable scheme, then you can look at constructible sheaves for the Étale topology. That's a reasonable approximation to the topological story because, you know, the Étale topology of scheme over the complex numbers, if you're, I don't know, finite type or something, then the Étale topology is very close to the classical topology. The sheaf theory, there's a good dictionary there between the different kinds of sheaves. So we're going to look at constructible sheaves for the Étale topology. And what Peter and I and Saul Glasman showed is that constructible sheaves for the Étale topology are the same things as functors from a certain stratified homotopy type. So they are also of this form right here. Now, again, you have to be a little careful because you have to say profinite homotopy type, but putting that aside. Okay, and as we just learned from David Ayala, we also have this example where we're looking at constructible sheaves on the entire site of singular n manifolds. And this is this construction of this amazing homotopy type BSC. And then he had sort of sub-examples of this, but I wanted to put this single example in front of us. So there's this sort of table of analogies is going here. So what do we have here? Well, we had the unstratified nonlinear story, and now we have the stratified nonlinear story, and that's on some sort of footing. There are a lot of open questions here, but the broad outlines of the story are clear. But we also had the unstratified Tanakhian duality story, the thing in green up at the top here. And the question is, what should the stratified Tanakhian picture look like? And that's the thing that I want to address next. And that's one of the projects that I'd like to propose we contemplate. So what's the basic object? The basic object is a stratified derived stack. And your very first question should be, what the hell do I mean by that? I have only provisional definitions for you right now. And I'll explain why in a minute. But roughly speaking, what I would like is a derived stack. So again, a FPQC sheaf over connective affines. And I want a stratification on it such that the strata are all gerbes in the sense up here. And then the basic model that we're looking for, the basic kind of category that we want to equate with our examples, is that of quasi-coherent sheaves on that thing. Right, so we want to look at quasi-coherent sheaves on our stratified derived stack. Now there's good news. The good news is that quasi-coherent sheaves on a derived stack, with or without stratification, is something that we understand perfectly well. And not only do we understand it perfectly well, but there's already a form of Tanakhian duality that tells us something about that collection of infinity categories. And that's the sort of Lurie style Tanakhian duality. Now, Lurie style Tanakhian duality, what it does is it provides for you a fully faithful functor from derived stacks. I'm not saying the word stratified right now, into a certain class of symmetric monoidal stable infinity categories, satisfying, and then you have to do something to try and pick out the ones that correspond to scheme morphisms, or sorry, morphisms of derived stacks. And there are various ways to do that, and Jacob in section 9 of SAG, sorry, chapter 9 of SAG, fleshes out different ways to do that. The problem is that he sort of provides for you different fully faithful functors, but there's no kind of recognition principle for the essential image of those things. So in the story that I was telling you above with the Tanakhian duality, what I was telling you was that you constructed a certain category that you were interested in, and often the way you built that category was you were thinking very carefully about a certain kind of cohomology theory in algebraic geometry, and you constructed from that a category, and then you attached to that category a derived gerbe, and that's how you constructed these interesting sort of different kinds of linear homotopy types, as it were. And so the question is, how do we do the analogous thing here? That is to say, how do we understand the essential image of that fully faithful functor from derived stacks into symmetric monoidal categories? And I don't want to try to answer that question in general, because I don't know how to do that necessarily. But in the case where you actually can understand a stratification already on your derived stack, in which the strata are gerbes, then I'd like to say that you just want to glue together the sort of traditional Tanakhian duality, traditional in the sense of unstratified, but still derived Tanakhian duality. And you can put those pieces together using the kind of recoulement tricks that we've heard about from Peter and David to construct a stratified derived stack. So let's see, I'm seeing two chats here. The sheaf of spaces, yes, exactly. Good. So, okay.
Quick question, I guess. When it's going to be stratified, should we think of these as like, I mean, I know we should think of them as sort of stratified spaces, but will they literally be sheaves of infinity categories with a sort of stratification where the strata are spaces again? Is that sort of the idea?
No.
No.
And that's the thing that that's the first thing that is kind of a little strange about this. You might have expected me to say something like I was going to look at sheaves of stratified homotopy types, and that's not what I'm going to do. And the point here is that what you're looking at is you're looking at sheaves on affines. And the affines themselves are going to supply us with the ability to stratify. They're going to supply us with the information of how to stratify. In other words, speaking of an affine always includes a kind of poset direction, which is this sort of specialization poset. And that's actually going to be where the stratification comes from. Should I say more about that? Probably.
Could you actually,
Yeah, I'd like to hear about it.
could I ask a maybe related question that you could answer even at the same time? You said that you wanted to think whatever the heck a stratification will be, it'll be like locally a gerb.
Yeah.
What's like a very simple example of that, just to ground myself, say for an ordinary scheme or something?
So, so perhaps
just like unpacking that definition, I guess. You know, locally connected, etc.
An example of a gerb. So, what do you want an example of? Sorry, I wanted to make sure.
Yeah, I guess. Yeah, a very like a non-derived example of a stratified scheme being locally a gerb, just so I can put those two definitions in the same box in my head.
Sorry, being a gerb is a local condition.
Yeah, and I don't know how to think about it, so I guess that's what I'm asking for.
Well, so okay, so you just want an example of a gerb, therefore?
Sure, but and perhaps one coming from a stratified ordinary scheme. Because I thought you had said that that was your expected definition for a stratified derived stack.
Yeah. So let me try to say let's not worry too much about the gerb thing. So I mean, okay. Let me just say the following. So a gerb has the following property. So if X is a gerb over K. So if X is a gerb over spec K, then what happens is that after some finite extension of K, then this thing will become a BG for G, an affine group scheme. So this is the kind of example that you should think about. So here G is an affine group scheme over K.
Uh-huh.
X might not quite be that. X might not have any K points, for example. So X might not quite manage to be a K group scheme. But the point is that after some base change, it will become that. And what this corresponds to on the category side is that you might not have a fiber functor over the field that you're interested in. It might have to happen only over an extension of that field.
Gotcha.
Right. So this is the kind of thing that I'm talking about. This is the kind of thing that I mean by a gerb. And in fact, for maybe at the level of specificity that I'm operating right now, maybe this is enough of an example for us to talk. So I mean, I'm really, I would like to think about BGs. And so an example the idea that I'm trying to sell you on is something like the following. So this is my picture of spec of ZP. And I've got 2 points here. This point here is the closed point, so it corresponds to spec of FP. And its complement here is also just a point, even though I've drawn it like it's more than that. It's also just a point, and that corresponds to spec of QP. And so the question is, well, if you've got a Tanakhian category over QP, and you've got a Tanakhian category over Z over FP, what kind of information do you need to be able to splice those two pieces together? How can you glue those two things and assemble them into something that lives over all of spec of ZP? Are you buying this yet?
Okay, yeah. So am I right that you're stratifying your scheme, in this case spec of ZP, but the The gerbs are the things that are getting reconstructed, not the scheme itself.
That's right. The gerbs are the things that are being reconstructed. So over spec of
that had been
QP,
my confusion. Yeah.
Oh, okay. I'm sorry. So right. So over spec of QP, I have some group BG. This is the thing over QP.
Mm-hmm.
And over the spec of FP, I have some other gerb. Let's say it's BG prime over FP. And what I want to do is I want to assemble those two things into a global object. And that global object is going to be some sort of derived stack. But there's a funny thing about the way this derived stack is going to be reconstructed, which I want to talk about at some point. But that's the loose idea. The loose idea is that I want to glue these two pieces together in a meaningful fashion. And I want to be able to say what happens on the categorical side, and I want to be able to say what happens on the derived stack side, and I want to be able to match up what happens on each side as we stratify. And let me just say, why is this important? Well, I mean, so, you know, we have mod P cohomology theory. So for example, you can look, if you're looking at a, let's say you're looking at a variety of characteristic P. So you can look at mod P cohomology theory. So you can look at cohomology with coefficients in FP, right? So a tall cohomology with coefficients in FP. And then what p-adic Hodge theory is trying to do is it's trying to give you a way of sort of fattening that up, that cohomology theory up, along with all of its relevant structure to something that's happening over this spec of ZP. And so, you know, I'm not going to try and recreate the diagram, but, you know, if you look in Schultz's notes, he draws like sort of a fat point around this sort of tiny point here. This is a terrible diagram, and I apologize, but that fat point is exactly the thing that I'm trying to construct here. Are you buying this?
Yeah, I see. I see my confusion, definitely. And so the connectedness is just to have this sort of basic bar cobar type correspondence.
Yeah, that's right. That's right. That's exactly right. Yes.
And does that literally hold? Just like if you're connected and pointed, then you are BG for some group scheme?
If you're connected and pointed and you're a gerb, then you are in fact a BG. That's right.
Okay, great.
That's right. And everything is locally connected. And so, yeah. Right. So, okay. So what are some examples of this? Well, I mean, I think there's a whole lot of these. I mean, one class of examples should come from just trying to linearize the story that Peter and I told about constructible sheaves over a scheme. So if you look at constructible sheaves over a scheme, then, oh, sorry, maybe I should give the first example, which is the topological example, which is already clear. So you can look at constructible sheaves for a nice stratified space, but with k-linear coefficients. And when you do that, there should be a corresponding stratified derived stack. And this will be a massive object. This will be way oversized in the same way that it was oversized when we talked about this object up here. This is just going to be too big. So you'll cut it down in various ways to try and get something that's more reasonably sized. But nevertheless, such an object should exist. But let me make a point about how this works. About how this gluing story works. So let's see here. Let me just make a point here, which is the following. So let's say that I'm just stratified over two pieces. Let's say my topological space only has two pieces. So I've got a closed piece and an open piece. And so the story is, Peter, is this backwards from the way you like to have it?
No, this is the way I would try.
Okay, all right.
For constructible?
Yeah.
Okay.
So I'm going to look at locally constant sheaves on, I'm going to look at constructible sheaves on X. And those are glued together from two pieces, locally constant sheaves on U and locally constant sheaves on Z. Right, and so this one's called I and this one's called J. And let's write down what we have. Well, you have, it's already wrong. You have I lower star. You have I upper shriek. Sorry, this is supposed to be a shriek. And you have I upper star. And over on the J side, well, what do you have? You have J upper star. You have J lower shriek. And you have J lower star. And this is a Recollement diagram. I'm talking about constructible sheaves, say, in K vector spaces, or the derived category of K vector spaces. So you have this Recollement diagram. But now there's a thing that's quite creepy that's going to happen. So let's talk about the creepy thing. So if we believe the story of ordinary Tanakhian duality, then what we believe is that we've got an equivalence between, say, locally constant sheaves and quasi-coherent sheaves on some object that I'm just going to call pi of z to be very rough about this, right? And so this is supposed to be some sort of derived stack over a field. On the other side, well, I'm supposed to have the same thing going on. So this is pi of u. And my stated goal was to have something like QCO of something that I want to call pi of x. But now something kind of funny is happening here. When I look at this kind of funny thing, I should have the same Recollement picture that I had above. But quasi-coherent sheaves don't satisfy a Recollement in this direction. They satisfy a Recollement in the opposite direction. So at the level of stratified spaces, you know, I have the open and the closed. This one's the open, and this one's the closed. But down here, it's flipped around, and it's flipped around in the following sense. Here, I do have an open. And on this side, well, I don't have quite a closed, but I have sort of a nil thickening of a closed. In other words, what I'm saying is that the relationship of pi of z and pi of u to pi of x is flipped from what it was before. I'm saying that you have pi of z, which sits in as an open of pi of x. And then, well, I don't quite get to look at the complement of that thing, but I instead look at this thing, which is I need to find a new notation for this. Maybe I'll do it like that. So this is a nil thickening of a closed. In other words, another way to say the same thing is that I'm looking at quasi-coherent sheaves on pi of x that are set theoretically supported on this pi of u, on this nil thickening of this closed. And that's what this category should correspond to. So there's a funny duality here between the sort of story that we got used to when we were thinking about constructible sheaves and the way to decompose those along a Recollement, and the sort of wrong way Recollement that you get on the category of quasi-coherent sheaves. So this story kind of reflects a certain sort of duality, which I don't pretend to understand, but I want to explore.
So I was thinking about this with David Gepner, actually. So I think this is because somehow when you take the category of quasi-coherent sheaves on the scheme, and you take the, so you trying to reconstruct the scheme from that, you're actually reconstructing naturally the Hawkshire dual of the scheme rather than the scheme itself. So this flips the roles of open and close for Rickleman in particular.
I absolutely agree with you, Jay. Yeah, that's exactly what I think too. I mean, I think this is a really, I think this would be a really fun thing to try to unpack and understand properly. So I started to write a paper. You'll see that I only started to write it. I didn't really get anywhere with it, which I'll share with everybody. But I think, you know, there's a key issue here, which I think is going to be, so I'm trying to write, what I started to do is I tried to write down the analog of what Peter and I did in the Ecology book. And the story that I'm trying to reconstruct is this picture of the fact, and this is something that came up in David Ayala's talk, is that you don't, if you want to understand constructible sheaves on some big thing, on some big stratified thing, then you want to understand local systems on each of the pieces, and then you want to understand on each of the strata, and then you want to understand local systems on all the links. And if you have an understanding of all those pieces, then you could reconstruct the whole thing. You can rebuild the entire category of constructible sheaves. So you want to be able to say the same thing, but now in this Tanakh dual side of quasi-coherent sheaves. And so what does that mean that you want? That means that you want to be able to understand the link inside the context of one of these wrong way recollements. And the question is, what is that? So in the story that Peter and I cooked up when we were doing this with topoi, and we were thinking of constructible sheaves, we were able to construct that thing by taking the oriented fiber product of two topoi. And this is, you know, this is the thing with the universal property that it's, you know, a pullback, except it's got a 2-cell in the middle of it. So I was just proceeding by analogy, I was trying to write down what the oriented tensor product of symmetric monoidal stable infinity categories, or maybe pre-stable infinity categories, should look like. And I think it's absolutely critical to try and understand that sort of décollage type description of this, of these stratified objects, because if we can do that, then I think we can actually get access to these things in a way where we'll have these formulas like the beautiful one that David wrote down, where you actually are representing constructible sheaves as a limit of categories of local systems. On this side, you're going to look at quasi-coherent sheaves on this stratified guy as a limit of quasi-coherent sheaves on each of the individual pieces. But those pieces will include some of these more exotic links. And that's the picture that I want to write down. So that's where I kind of want to start with this. So that's one problem. Maybe I shouldn't go on any longer because I guess it's already 2:10. I have a lot more problems here, but let's come back to that soon. So this is where I wanted to start with this stratified Tanakhian duality, and I wanted to see what people thought about it. And
so I guess I have one last question about your last row.
Yes.
So do you think constructible sheaves with transfers will play any role like you see for G spectra, for instance?
Yeah, I don't know. I've been trying to understand that. I wish I had something intelligent to say. I definitely see that constructible sheaves with transfer I don't have a sense of how those transfers, I don't have a narrative for you about how those transfers should interact with this picture. and if somebody does, I would love to hear it, because I just am not. Sorry, I'm a dope, but I just don't know the answer to this question. It's a really good one. I think it's really important. I just can't answer it.
So you may have more success sort of in the situation of a stratified Derive stack where you literally are, well, where the strata are these, well, group schemes, right? Or classifying spaces thereof?
Yes.
Okay.
I think, you know, in the same way that neutral Tanakhian duality is easier than non-neutral Tanakhian duality, I think, you know, it'll be easier for us to think about it in that case to start off with. But just as a psychological crutch for now. Yeah.
So it sounded like you, am I right? You were just talking about, or a sub question here is just for a plain old recollement of symmetric monoidal presentable stable. You want to recognize the middle term as some sort of tensor product specifically. I mean, there, you know, there's already the reconstruction as a fiber product, which uses category theory. I'm not used to the. It feels like that's part of this duality, is going from fiber products in topoi to like tensor products algebraically. Is that right?
Yes, that's right. So the fiber product, right. So yeah, let me draw a picture if I can. Let's see here. So wait, that's the wrong way around already. It's, you know, it's bad when you've written down one symbol and you think you've already made a mistake with drawing it.
Maybe it was in the wrong part of the page.
So this is the Topos diagram for a second. So here's the Topos diagram. So I have the closed piece and the open piece. And what do I have to do to reconstruct the whole thing? To reconstruct the whole thing, I'm going to try and write down the deleted tubular neighborhood of Z inside of X. And that's going to tell you how to glue U and Z together, right?
Mm-hmm.
And so that is literally the oriented fiber product in the category of topoi.
In what sense is that a deleted, like if they're topological spaces, what does this recover?
If they're coherent, spectral topological spaces, then it actually recovers the deleted tubular neighborhood. If they're something like Hausdorff spaces, this isn't gonna be a very good analogy. Because as soon as you get Hausdorffness involved, this kind of oriented fiber product kind of degenerates, so it doesn't really help. So this is really something about spectral topological spaces.
Sorry though, isn't W going to be, if you just have a stratified space over the post set 0 to 1, it's going to be the link?
It's the link. That's exactly right.
But in the Hausdorff case, is there something funny that happens when you take the link as this sort of section space and look at sheaves on it?
It's just not the oriented fiber product.
Oh, okay, sure.
I'm using a particular construction in this context. So let me tell you what Peter proved, and is in the Topos theory, the exodromy paper, which is the following. So remember, how do you do the recollement, right? How do you form the recollement of U and Z? Well, what you're supposed to do is you're supposed to use the gluing functor. And, the story is that a sheaf, and in fact, I mean, a really constructible sheaf on X is the same thing as, a local system L on U, a local system L on Z, and a map from LZ to I upper star J lower star LU. right? That's how you reconstruct sheaves on X from these two pieces. Right, that's the story. And well, what's the point here? The point here is that what Peter showed is that the base change is valid for any of these things, is valid for any of these squares. That is to say that if I look at I upper star, J lower star of anything, then that's the same thing as G lower star of F upper star of anything. And so that means that you've re-expressed this guy as a G lower star, F upper star, LU. And that little move turns out to make all the difference when you're trying to analyze the, the way that you want to reconstruct. Now you can reconstruct X just from the information of W by taking kind of an oriented push out.
Yeah, maybe a sort of tangential remark for people who like algebraic geometry is that, so, I mean, Deligne sort of introduced these oriented fiber products of topoi because, well, in a sort of slightly different setting where I is allowed to just be sort of any morphism and J is the identity, this is really the natural target for the nearby cycles functor. And so you can obtain the sort of classical nearby cycles functor when you're working over spec of a DVR from a specialization of something that just is given to you by this picture. But like in this setting, this sort of base change theorem is quite useful. And so, I mean, like Gabor proved this in some special case to do some stuff with moving around nearby cycles functors.
So this, I mean, this is a, so the idea now is that this W here, this oriented fiber product is really going to play the role of the link. And so I want the role of the link in the same way in the world of quasi-coherent things. So, yeah. So if I want to look at quasi-coherent sheaves on pi z, now that thing, I'm sorry, Peter, is embedding in an open fashion into quasi-coherent sheaves on pi x. And now this dual thing is like a formal thickening of a closed. And the kind of thing, I've written these arrows in the direction of the lower stars. The upper stars are the symmetric monoidal functors. All right, and in general, the lower stars are going to do things like satisfy the projection formula. And so what do I want here? I want something like an oriented tensor product. The orientation is going to go the other way. The map's going to go up like that, but that's what I'm going to try and write down. Well, that's one thing we could try to do. I don't know how to define this object yet, so that's the question.
So I think going back to Aaron's original question, he was saying that QCO pi x is this right lax limit of the gluing functor, and what you're trying to do is construct the appropriate lax co-limit.
That's right. That's exactly right. Is that what you were saying, Aaron? I'm sorry.
Yeah, that's exactly right. Jay and I have been thinking about symmetric monoidal recommense as well. So, yeah.
Yeah. So I mean, I think such an object should exist, and then it should allow you this sort of décollage perspective on these kinds of stratified objects. And then, you know, by kind of working, I mean, one of the sort of miracles that David found, and one of the miracles that Peter and I found, is that the décollage perspective allows you to take a priori very complicated object like a stratified topos and break it up into pieces, all of which you could easily comprehend. It sort of turns everything into fancy diagram on the subdivision. I guess, Aaron, you spent a lot of time thinking about the subdivision as well.
Yeah. So this is the version that is about simultaneously about QCO, but having nothing to do with a directed tensor product. That's what I'll be talking about on, I guess, in a week. And I guess for us, the gluing data is just a composite functor, I upper star, J lower star.
Right.
And there's certainly no intermediate object that is like a spanning term, like what you're describing.
Yeah.
Yeah.
Yeah. And
but then the strata are, you can well, there's still a reconstruction from strata picture.
Yeah. So the reason that I wanted to try to say it this way, well, okay, so there's lots of reasons to say all of this, but I mean, one thing to think about here from this picture over here is that, well, so, I mean, one thing that we all have to do is we all have to go to your talk and understand what you're saying. And I have to read your paper again. But I think, one of the values of trying to have this perspective would be that if you had a décollage of these gerbes, then you could try to just apply QCO to all of them, and you'd have a décollage corresponding in this direction.
I've got a dumb question. Is there any reason why this sort of directed tensor product doesn't exist for formal reasons? Like, it seems like the kind of thing that might sort of drop out of some abstract nonsense.
It would surprise me if it didn't exist just for formal reasons, but
you want to understand it as well?
Yeah, I want to understand it. I don't just want to understand. Yeah, absolutely. I want to understand it.
Okay, all right. Because I was worried.
I agree with you. I mean, I think that, for example, you just need to know that the following kind of cotensor exists. So one is just the category with two objects and a morphism from 0 to 1. And if I just take any stable, presentable, symmetric, monoidal infinity category that's, if you like, generated by perfect objects under filtered colimits, that such an object exists.
Are you sure you don't want it to be like a tensor, or I don't know, there's some weird sort of contravariance.
Yeah, all right, yeah, fair enough. I'll write it in that orientation instead. Yeah, but now I don't know what symbol to use. There.
Great. Yeah.
It's not, it's not just the tensor product in presentable categories or something like that. You're not taking one, turning it into a presentable category, and then tensoring it with A. It's a much more complicated structure than that, because this is supposed to be, the external cotensor of symmetric, monoidal, presentable, blah, blah, blah categories with categories. So, I mean, I don't, if you had such an object, then you could construct everything else just using the existing tensor product. Yeah, but I mean, the key case that you'd want to understand this thing is in the case of modules over a ring spectrum. If you knew how to do it for that, then I think, various representability theorems would tell you how to get it for anything. But yeah, I don't have a clue how to compute it.
So symmetric monoidal functors out of this colimit preserving are supposed to be arrows in symmetric monoidal functors from mod R?
Yeah, thank you. Yeah, that's exactly right. So if you want to look at, sorry. Yes, the statement is that symmetric monoidal colimit preserving functors from one tensor A into B should be the same things as, well, I'll just say it kind of coarsely, natural transformations in this guy, in symmetric monoidal functors from A to B. Yeah, that's exactly the kind of thing I want. And so this would be the oriented tensor product. And I really don't know which direction to draw the arrow now that I've said it like this, but let me just draw it in a direction. The oriented tensor product of A with A over A.
And that you're sorry, you said that that should be an instance of this like link.
Well, the link is what happens when you have a closed in A and a or sort of thickening thick closed in A and a complementary open, as it were. And then you take this construction and you tensor it on either side with those things. Should I write that down?
Yeah.
Page below. So what happens in topoi is the following. So the only reason I keep going back to topoi is that I remember that story perfectly. So I have to keep reconstructing it from that. Sorry. So to get this guy, what you do is you can take X, oriented fiber product over X with X, and then you can cross this X with Z, and you can cross this X with U. And so I'm going to just try to do the same thing.
The arrows are happening in X.
Yeah, that's right. The arrows are happening in X, so I just tell you where the endpoints need to live. Right, because they're sort of paths that go from Z out into U. They're those kinds of exit paths. So first I'm just going to take paths, that's what this part says, and then I'm going to tell you where the paths have to begin and end. And so I'm just going to try and do the same thing, not really knowing that I can. So I don't know, I'm choosing letters at random, so sorry if this is poor notation, but I'm looking at paths as it were in A, and then I'm telling you they need to start at B and end at C. And that this would be the sort of analogous thing that we'd want to have as our link inside the world of, inside this linear stratified world.
So do you expect this to sort of be the thing without sort of assuming any sort of coherence or whatever? Like, you know, in the Topos story, the oriented fiber product is sort of the same no matter which place you take it, I guess?
Yeah,
Whereas
that's right.
The co-product that matters where you do it?
Yeah, so you're quickly verging on the territory where I'm going to very rapidly get myself confused. But yeah, so let me say the following. So I think, you know, the place where I want to operate, well, I'm prepared to be shouted down on this. I'm making a choice here, and the choice could be made differently. But I'm interested in what are called complete Grothendieck pre-stable categories. By the way, I'm going to implement what I call seminar conventions now. So category always means infinity category, and everything is implicitly derived. So these things are described, they're described in an appendix of SAG, but which one? It must, is it D or C? Does anybody know? Peter's not here. Peter would know instantly.
Well, it's the one called pre-stable. I've taken a look at
C
that.
or D. I'm not sure which one. Anyway, so these complete guys, these are the things that naturally arise as QCO of stuff, right? So when I take QCO of like a quasi-geometric stack, then it's always, sorry, the connective part of QCO, then it's always in here. I think the stability is effectively a red herring, because in the Tanakhian reconstruction theorem, you have to say that your functors preserve the connective objects anyway. So it doesn't seem like it does you any good whatsoever to pass to the stability. Again, I'm prepared to be wrong about that, but that's what I see. Yes, these are complete growth and pre-stable categories, and the maps are symmetric monoidal. Sorry, I should have said more. Complete growth and pre-stable categories. The word symmetric monoidal has to appear in here. I'll just write it there. And the maps are going to be symmetric monoidal, co-limit, preserving, compact functors. So I don't know, maybe my notation has to reflect the compactness of the functors. But anyway, this is my proposal for like something analogous to the category of coherent topoi.
So, dumb question here. It's not the case in this setting that compactness, like preservation of compactness, is automatic because you preserve the unit or whatever, like in some other cases.
No, the unit in general. Yeah. So this is another issue. This is the kind of decision we're going to have to make in the course of this project. But one thing that is kind of annoying is that the unit isn't always compact. So an example of this is if K is a field of characteristic P greater than 0, and you look at BGA, and I look at QCO of BGA. So these are, representations of GA. So it's a pretty mild object, but here the unit is not compact. Grothendieck does not imply compactly generated. Just to let you know.
Does it imply, presentable at least?
It does imply presentable, but it definitely does not imply compactly generated. Okay. And that's part of the issue. So, in these kinds of examples here, you have this split between, perfection and compactness. And so you either have to say that you don't like those examples, which is fine. I think that's a position you could take, or you have to say that you want to include those examples, but then you have to be a little more careful about what you mean when you talk about these categories. So by the way, what does compact mean? So compact means, so we're talking about a functor that looks like an F upper star. Compactness is the same thing as saying that the lower star, which is the right adjoint to the upper star, preserves filtered colimits. That's what compactness is.
So, dumb question. I thought that this kind of thing only happened when you were looking at like QCO of schemes that weren't compact, that weren't coherent, or something like that.
But what kind of thing could only happen with?
Where you're not, where perfection is different from compact objects or something.
So for schemes, that's right. For schemes, you always, as long as your schemes are reasonable, you always have this. but for stacks, it's just not true. Perfection and coherence start to separate from each other, and this is the example to contemplate. And it's not, I mean, unfortunately, it's not like it's a, obviously pathological example. I mean, the affine line's a little weird in characteristic P, but it's not so weird that we should be. I don't know. To me, it doesn't look like the kind of example I would want to exclude, but, Wow, so when David was talking, there was like 30 people in here, and now there's nobody. Sorry, I drove everybody away.
No, there were 19 people here at the beginning.
Oh, okay. I feel bad.
And
we are getting towards 3 hours. Yeah.
Yeah. I guess you'd report. Anyway, so this is the basic set of ideas that I wanted to put in front of people, and
So does this stacky problem happen in characteristic 0 as well? Like,
no.
Can you? No, it doesn't.
No. I can't remember what the right theorem is, but or the right statement is, but it's a theorem of Drenfeld and Gatesgory, that if you're in characteristic 0 and you're I'm not sure what the right adjectives are, but you're a reasonable Artin stack, then the unit will be compact. This is a strictly characteristic P phenomenon.
So I guess the question is it worth looking at this question first in characteristic 0, getting a feel for sort of how things should go, and then sort of trying to massage the other case where the category of stacks that you're looking at is sort of weirder?
So I'm of two minds about that. I don't want to restrict to characteristic 0 forever, certainly. Just because, in the kind of examples that I was thinking about over here, somewhere over here, like this is the example that I'm dreaming about the most. I really want things that are of mixed characteristic.
I do think that sounds reasonable, though. Nick likes to joke that it's the separation of problems of algebra and problems of analysis, within the context of derived algebraic geometry, of course.
Yeah.
But analysis being things like compactness, as it always was. Intco, blah, blah, blah. That sort of thing. I mean, the question of an oriented tensor product that's a pure algebra problem.
That's a pure algebra problem, I agree. But I think the question of you could try and do the oriented tensor product. Right, okay, so maybe this is what I want to say. If you would prefer to work with what you might call perfect, I don't know what to call them, perfect Tanakhian categories or something, then you could work with complete Grothendieck pre-stable symmetric monoidal categories. The maps are the things I said, but then you'll also add in a condition that they are compactly generated by their dualizable objects. Right? So we might call these the perfect Grothendieck pre-stable categories. And you could try and run this whole program there.
Yeah, I guess so. The motivation that I sort of had for asking this question is, when you're looking at, I don't know, K-theory, right? And you want to talk about the tensor product of these stable infinity categories. Well, first, when you want to talk about tensor product of stable infinity categories, first you ask, well, what about when they're perfect first? And then sort of, can you extract the general case by looking at sort of the restriction of that thing, well, sort of like the subcategories when you embed them in a perfect thing. Does that make sense, or I don't know?
It does. I'm happy to make that restriction for the purposes of writing some stuff down. But I guess I would be really unhappy if we veered too far away from this class of, from examples that I
Yeah,
will always want
absolutely.
to return to this kind of example. That's what I want to say.
Yeah, absolutely. I guess the question is like, maybe there's like a perfection of such one of these sort of growth deque free stable infinity categories, and then
I'd be
you
pessimistic
have an
about that.
embedding or something like that. I don't know.
I'd be very pessimistic about that.
Okay.
I'd be very pessimistic about that. Yeah, I don't see a way to consistently reduce to the perfect case. I think I would be surprised if you could do much of that.
Okay.
But I mean, I take your point. It's just a lot easier when you can assume that you know, compact equals perfect and everything's compacted generated. That life's just easier. So I don't know. I'm willing to cede ground on that.
Yeah, I don't know. I was just wondering if there is a reduction, then it could be helpful. But if you don't think so, then
yeah,
I don't know.
It doesn't feel like it's going to be possible. I'm always prepared to be surprised, but it doesn't feel that way to me. So what do you, I mean, you have to answer now, but I'd like to know what your thoughts are about this kind of project. And if so, you know, what aspects of it you might be interested in, how it ties to stuff that you already know. I guess we'll hear a lot about that from Aaron, because he already knows at least part of the story in detail, I know. But
yeah, I'm curious. Maybe we can talk more after I talk next week, but the role of the links, whether it's sufficient to just have functors around.
So I don't know if this is relevant, but I'm actually giving sort of an exposition of this theorem of Aaron, David, and Nick tomorrow in the MSRI seminar.
Oh, great.
In the equivariant case, right?
Yeah, yes, that's right. Though the formulation and proof is, as you know, quite general. I just give the equivariant case to give an application, basically. The proof is sort of categorical and not algebraic in nature. I think it's a bit different from the one you wrote down. It relies on properties of the Lax-Right-Con extension, a formula for the pointwise right-Lax-Con extension, essentially. But it may be.
I couldn't imagine that being like fundamentally different.
No, I think it's
perhaps
the same sort of, it's the same sort of inductive argument.
It must be. Yeah.
You stitch in strata one at a time.
Mm-hmm.
Anyway, it's potentially relevant to the topics we're discussing at the moment. So.
Yeah, that's great. Thank you, Jeff.
Yeah, I'm looking forward to that.
Yeah, that'll be fantastic.
If you want to post a link to it and sort of what time it is, that would be helpful in the Slack. Just because, yeah.
Oh, sure.
I don't have the links to any of.
Oh yeah. So it came out in the MSRI announcment, but sure, I can post the link.
Well, yeah.
I got it right now.
Harry's not officially here, so
ready.
Yeah.
There it is.
But pursuant to your point, Aaron, I mean, you know, I realize I'm going to be saying this to someone who already understands this point very, very well, but you know, there's this, you know, and I'm going to get Cartesian and co-Cartesian mixed up, so just forgive me on that.
Sure.
So locally co-Cartesian fibration down to your poset is the same thing as certain kind of Cartesian fibration down to the subdivision satisfying some stuff.
Mm-hmm.
You know, and these are in the cases where everything's got limits and co-limits, that kind of thing. So and this is that relationship is the relationship that allows you to replace just the straight functor I upper star J lower star with a span that goes like that in a systematic fashion. So that's like the I don't know what I want to say.
Right.
It's like the linkification or something. I mean, it's like you're starting to inject all the links that you need in order to write that down.
So
That's how I'm envisioning this anyway.
I've got a stupid question. Have you looked over, I mean, so sort of the construction of this, for the Topos case, the construction of this exponential by one is sort of pretty complicated. And I was wondering, do you think that there's anything to glean from that for this question? No?
You know, it depends on how you think. That's not a very fair question, but you know, so if you could, you know, the Topos case is the sort of it's the non-linearization of the linear story. So you think of the story as a k-linear story, and then you think about the characteristic of that field going to 1, and that's supposed to be reconstructing for you the Topos theoretic case. That's the story that's in my head anyway. In the same way,
right.
You know, Tanakhian duality over F1 is Galoisian duality. That's the
right. Yeah, no, I mean something like way stupider than that. I'm talking about just the construction of this oriented tensor product, right?
I know, but I'm coming around to a point, and the point
okay.
is that if you look at that description and you see something that is like, okay, so here's a stupid example. So if I look at functors from let me just make sure I'm saying this correctly. Functors from a category A into the category of connective spectra. That's one of these Grothendieck infinity categories with all the properties that I was giving. And then I think, I'm not sure about this, but I think what should happen is that this guy, I'm not at all sure about this, but so if I'm wrong, please let me know. But I think you should be getting this. That's the formula, at least, that happens in Topoi, and I think the same formula should happen here.
That looks right to me, actually.
So I think one thing you could try to say, if you felt like it, is that like this is what you get for the functor categories, and everything's a localization of a functor category with some list of nice properties. So this is what you get. I mean, you can probably give a statement that this thing exists in general by doing that.
I mean, that's useful. Yeah.
But I don't know how to use that. And I mean, I don't know because I haven't thought about it very much, but I don't yet know how to do that, use that to construct this guy, for example. And I would like a very kind of hands-on description of that category. That's sort of the monogenic case. So I feel like I don't know. I feel like it should be easy to understand. I'm not sure if it will be, but it's.
I mean, is it so easy to understand the Topos case? I mean, at the level of the site, I guess it's not so bad. But
you have a similar description of the oriented fiber product in the pre-sheaf example, right? That's what you were sort of building off of.
That's right. That's exactly right. So in the Topos case, this is the sort of thing that you understand. I don't know. I feel like, well, one thing to say is that I feel like this is definitely the kind of thing where I would just naturally write down the wrong thing, and I would need someone to rescue me from saying bullshit. So this is one place where where I would really look to you guys to keep me safe.
yeah, I mean, so if you could show that this thing existed sort of for abstract nonsense reasons, then like you do at least have a good description of it when you throw it into the Hom functor, right? So that's like helpful, at least understanding it, even if you don't have a sort of like on the direct level description of it. You have like a sort of unit understanding of it, kind of.
Right. That's right. That's right. Yeah. I mean, I already have it. Once you know it exists, this is a lot of what you would need. But you know, for example, I mean, I'm just relying on my experience with Topoi here. There's several points that are kind of hard, right? I mean, you know.
Well, yeah, that's what I was saying. The proof in SAG of this fact is long.
But it's not just that but it's not just the thing exists, but even once you know it exists, you need to have certain properties of it, and not all of those properties are completely formal. That's what I want to say. So it would be good to have access to some sort of description that's concrete, even if it's concrete in such a way that you can't do a computation. It's useful.
All right, cool.
In the same way that with the oriented fiber product in exogamy, you know, you can write down, if you've written down the pieces with generating sites, then you can write down a generating site for the whole thing. And that's a terrible, like in a sense, that generating site is not ever what you want to contemplate. But even just the fact that it's there is helpful to you.
So this is, I was just thinking about the more general stratified picture, and if you have a symmetric monoidal category stratified over a post set, you know, a priori the functors between strata are push all the way up to the full category, and then take pullback down to the new stratum. But there is a sort of minimal, like you can just look at the subpost set consisting of your two elements that you're looking at the monodromy functor for.
Yes.
And so at the very least, I still don't know what the oriented tensor product is, but at the very least, that reduces, I think, the full question of links, at least at a first pass, without laxness, to just this single Recalmont question.
Yeah, that sounds promising. That sounds like the kind of thing that I wanted to be true. So that's great.
Yeah,
that sounds excellent.
But am I understanding it is important that it's not just having some sort of like smaller object, some smaller symmetric category that the monodromy functor factors through, but rather specifically having it be base change, like the upper and lower stars have switched places?
Yeah, I think it's exactly critical that this be base change. Yeah, I mean, everything that we did relies on this being base change. And why, let me say something about why that should be the case. So let me just try and say it by talking about the shape for a second. So you remember the story with the shape. I'm telling you the Topos version of the story. So the shape was what you got by sort of pulling up and pushing down along these functors here. These are the global sections functors. Right, so the shape is what you get by pulling up and pushing back down, and that gives you a pro object in spaces.
Hain to the gamma.
Hain to the gamma, yeah.
Yeah.
So you pull up and you push down. So now what I want to do to get this linking, so what's the shape of W look like? This is the point that I was trying to get around to. The shape of W is, well, what you get by pulling all the way to W and then pushing all the way back down. But that's the same thing as pulling back along here, pushing forward along J, pulling back along I, and then pushing forward along gamma.
Sorry, could you just say that one more time? Maybe you were indicating by your mouse or
yeah,
something.
Sorry.
I didn't see it.
Let me try to be a little more thoughtful about this here. So I'm trying to understand the shape of this W.
Right.
So I pull all the way back to W and I push all the way back down.
Right.
Right, that's what the shape would do. And so you could, using this base change thing, you could rephrase that as pulling back along here, pushing forward along here, pulling back along here, and then pushing forward again along here. So now, now imagine that you had not just 2 of these, but 3 of them, and you were zigzagging them together, right? So now you have these kind of iterated push-pull, push-pull, push-pull type things. Right. So on the one hand, that's the composition product in pro spaces. But on the other hand, it's also just the shape of the link.
So you're saying that links of links have shapes governed by that composition?
Yeah, by the sort of staircase composition where you push, pull, push, pull, push, pull.
Cool. Okay, let's see.
And so, well, what will I say here? So I guess, yeah, I mean, that kind of analysis is absolutely critical for everything we do in the paper. So if we wanted an analog of any of that stuff in this context, I think.
What replaces the word shape?
Right. What replaces the word shape? What replaces the word shape is gerb of fiber functors. Now that's no longer just a, or at least it's not in any way that I'm aware of, just a push-pull. But it, you know that. Remember, how did that push-pull work? That push-pull worked to give you the shape, because what it did is it exactly controlled as it were, the fiber functors from U. Right, it's like you get a pro space whose objects are fiber functors on U.
But so whatever the heck W is, like you know it, or extracting the shape still amounts to J lower star followed by I upper star.
Of W, yeah, that's right. That's right. But knowing that you have, but you know that the advantage of that W is that you really now only have to worry about, like, so when U and Z are stone topoi, that oriented fiber, yeah, when U and Z are stone topoi, that oriented fiber product, that W is also a stone topos. So you're really looking at the analog of just local systems on W. And that's how you can reconstruct constructible sheaves on a scheme by taking just this limit of local systems on each of these pieces. Like, I'm sorry, the category of constructible sheaves relative to a fixed poset for the moment is the limit along the subdivision of these categories of local systems. That was the sentence I was trying to get out.
I see.
And that's, you know, this decollage picture is, you know, this decollage picture where you try and construct the tubular neighborhood is absolutely vital for that story. So if we want the same thing over here, as I hope we do, then yeah, I mean, I would want to have access to that deleted tubular neighborhood. I mean, by the way, I mean, a related question is that this oriented fiber product, in a handful of good cases, I have a description of it as arising from a scheme. But in most cases, I have no such description.
So you said that you have a description of it as coming from a scheme in the specific case of the vanishing topos? Is that right? I don't
No,
remember exactly.
no,
what you said.
not in general, not
Okay.
in general.
Or a simplicial scheme or something. Still no.
I have a representation of it as yeah, exactly. The vanishing topos I have a description of as a simplicial scheme. It's not mine. It's due to Cox, who was a student of Friedlander.
Mm-hmm. I mean, that's not horrible.
It's not horrible.
I mean, is it the sort of thing where in your nice cases that reduces to an ordinary scheme, or is it just okay?
Yeah, absolutely.
So I wonder if somehow the bad things are coming from the fact that the oriented fiber product is coming from you have the unoriented fiber product of topoi showing up in here, and that is sort of, I mean, as we've discussed, sort of badly behaved with respect to the algebra. I wonder about that.
Let's see. I think the answer is yes and no. So let's see here. So so how do you? So let's just do this deleted tubular neighborhood case. Even that, I don't think I have a good description of. But so I can form the oriented fiber product here. That's the path topos. And then I can just pull it back along this open, right? And so now all the other squares here are just going to be ordinary pullback squares.
Right. When they're open and closed, it's actually fine, right?
Right.
So
exactly. That's exactly my point.
Yeah.
So this is X cross over X with U. And so this is an open sitting inside here. And then here I have this guy.
And it's actually fine also when they are locally closed as well.
That's right. So this is that's okay. Thank you, dear. This is a locally closed sitting inside this thing, right? And so that part of the story from the point of view of I mean, that's a good, valid story at the level of schemes, assuming that you knew that this thing was a scheme somehow. So that's the problem, is that I don't have a geometric representation of that guy.
Even as a simplicial scheme?
I don't think I have one even as a simplicial scheme. I think in many cases, this is the guy that Cox understands as a simplicial scheme. But I don't think I have a general understanding of the other guy.
Even, I mean, I don't want to be completely stupid here, but I mean, X is a closed immersion in itself, right?
Yes.
So why can't, like, if you have a description of the thing on the left, you can't just play the same game and get a description of the thing in the middle, or?
Well, it's right. In order to answer this question, I'd have to remember what Cox's theorem says. So maybe we should look that up.
All right, cool.
Yeah, no, you have a very good point. Maybe there is a description of this thing as a simplicial scheme. If we just unpack what Cox does in this one simple example. I seem to remember that there's a condition, but maybe I'm being stupid. I can't remember. Sorry.
Yeah, we should take a look. We should take a look.
Yeah. Yeah. I mean, I think, the number of questions that I have is far higher than the number of answers I have about these things. Did you say something, Aaron?
No, I don't, I should have muted. Sorry, there might be people in the background.
Oh, that's okay. I just wanted to make sure I wasn't missing something. Yeah, so I will share with everybody the Hemi document that I started. I mean, it's literally got nothing in it, but I think it might help to at least sort of identify some And then we can see what kind of thing we might want to do from this.
Cool. Yeah, this is an interesting question. Thanks for bringing it up.
I've got a sort of really stupid question. So when we talk about simplicial schemes, like, you know, you can think of it as sort of like a presentation of some sort of stack or something. Like in this case, is it going to be like presenting something that's doing Mumford or anything, or no?
No, I don't even think, yeah, definitely not Deline Mumford, and probably it could conceivably be a geometric stack, but I just don't.
Ah.
I just don't know.
That would be nice. Who knows?
I just don't know. Yeah, I mean, I think the task is to figure out what that whole story. So I'll find the papers of Cox where we were talking about this. Peter, I bet Peter can remember precisely which ones we should be appealing to. Or actually, no, it's actually written. There's a reference to it in our paper, and we can try and reconstruct the story. I can't remember right now how it goes.
Yeah, no, I'll take a look. All right, thanks.
Yeah. All right. Well, I don't know. Should we try and do Friday again?
It's fine with me.
Do people like Friday at noon? Is that?
I like Friday. Yeah, Friday is good.
That's also good for me.
Okay.
Cool.
All right. Well, I'll propose it. If it gets shot down, then we'll do something else. But I'll pitch the idea, and then we'll see what happens.
All right, cool.
All right.
That's all.
All right. Lovely to chat with you guys. I'll see you soon.
All right, so
Yeah, talk
bye-bye.
to everybody then.
Bye.
Bye.